Hello everyone, welcome to Geology Wonders YouTube channel. If you have the first time to see this Geology Wonders YouTube channel, don't forget to like, share and subscribe to this channel. So today we can see about how to identify any minerals. Can we identify a mineral just by looking at it? You can see a beautiful golden crystal. Is it a gold? You can see a black minerals. It is hematite. You find a clear crystal. It is quartz. Not so fast. Mineral identification is much more than simply looking at a color. A mineral can change its color because of tiny amount of impurities. Two minerals can look almost identical but have completely different hardness, cleavage, strike, or density. In fact, one of most famous example is pyrite. Can you look remarkably similar to gold, but there are simple tests can quickly test you. It is a gold or it is a false gold, like pyrite. In this video, we are going to learn the 8 most important physical properties by geologists to identify minerals. That is crystal habit, cleavage, fracture, hardness, color, luster, strike, and specific gravity, and more properties of minerals. And at the end, we will also explore some special properties such as acidic reaction, magnetism, radioactivity, fluorescence, and phosphofluorescence. So stay until the end, because by the time this video finish, you will be able to examine an unknown mineral like a real geologist. Welcome again to Geology Wonders. Let us begin. Number 1, to differentiate mineral is crystal habit or a crystal form. Our first property is crystal habit. Crystal habit is the characteristics external shape of minerals and the way individual crystal or groups of crystal glow. But here is fascinating part. A crystal shape is controlled by its internal atomic arrangement. The atoms inside the mineral are arranged into or in an organized repeating structure. That internal structure influences how the crystal glows. For example, quartz. Quartz is one of the best examples. When quartz has enough space to grow freely, it commonly forms exolited or elongated six-sided prismatic crystal, sometimes terminated by crystal face. But quartz can also occur as a massive quartz, where individual crystal faces are not obvious. Same minerals, different habit. Okay? The same minerals have a different form or habit. For example, pyrite. Pyrite commonly develops cubic crystals. Some specimens show beautiful, sharply defined cubic. Other pyrite specimens occur as a massive or granular aggregates. The other example is garnet. Garnet commonly develop equidimensional crystals. Often they shape resembling a hadron or trapezohedron. These crystal forms can be very useful clue during identification. So remember that. Crystal habit is essentially a mineral characteristic growth shape. But what happens when we break a crystal? That is where our next properties become important. That is cleavage. Imagine habit, a mineral or hitting a mineral. Hitting a mineral with a hammer, will it break randomly? Not always. Some minerals have preferred direction along which they break. This property is called cleavage. Cleavage occurs because certain planes within a crystal structure contains relatively weaker bonding. When the mineral breaks, it tends to follow those planes. For example, mica. Mica has exactly basal cleavage. You can separate mica into extremely thin sheets. It is almost like peeling layer from an onion. Example 2 is feldspar. Feldspar commonly has two cleavage directions that meet at approximately 90 degrees. This is an extremely useful clue when distinguishing feldspar from quartz. The other example is calcite. Calcite is third direction of cleavage that produce characteristics of rhombohedral fragments. So, if you break a calcite crystal, you don't normally get flat cube like feldspar. You get inclined surface. Bonus example: halite. Halite or rock salt have three direction of cleavage at right angle, producing cubic fragments. So cleavage is not simply about whether a mineral breaks. It's about where and how the mineral prefer to break. And now we need to distinguish a cleavage from another property. It's called fracture. The other property is fracture. Number 3. Fracture describes how a mineral breaks when it does break along a cleavage plane. Some minerals have very distinctive fracture pattern. Example, quartz. Quartz commonly displays cohedral fracture. The broke surface can look like inside a shell with smooth curved surface. The other example is obsidian. Obsidian is a volcanic glass. It is not mineral because it lacks of crystal structure, but it commonly show excellent conchoidal fractures. Its sharp edge are one reason obsidian was historically useful for cutting tools. The other is sulfur. Sulfur can show an even or irregular fracture. Many minerals does not have a special fracture pattern and simply break into irregular pieces. So there has easiest way to remember the difference between the cleavage and fracture. Cleavage break along preferred planes. Fractures break it other ways. And this distinction can be extremely useful in mineral identification or classification. And the other one is hardness. Now let's move to one of the most important mineral properties of hardness. Hardness is resistance of minerals to scratching. And this is where geology become almost like a detective investigation. You can test an unknown mineral against another material. If a mineral A scratches mineral B, a mineral A is harder than a mineral B. Geologists commonly use Mohs hardness scale depending on this hardness developed by a German mineralogist, Friedrich Mohs. The scales run from 1 up to 10. The example 1 is Talc. Talc has hardness of 1 Mohs scales. It is extremely soft and can be scratched very easily. Number 2 is the other example is to Quartz. Quartz has hardness of 7. It is hard enough to scratch ordinary glass. The other one is diamond. Diamond has hardness or the 10th Mohs scales, hardest mineral on Mohs scale, but there are important field material you can see or can use when standard minerals are not available. A fingernail is approximately 2 up to 2.5 Mohs scales. Copper coil around 3. Knife blades roughly 5 up to 5.5. Glass approximately 5.5. Steel fill around 6.5. So imagine you have an unknown minerals. It scratches glasses, but it can be scratched by steel file. That immediately tells you that its hardness is somewhere around range between those materials. Here is another important point. Hardness is relating to atomic bonding. 3 important factors can influence bonding strength: atomic size, ionic change or ionic charge, atomic packing. This is a bonding or important points that have you seen. 3 important factors can influence the bond strength: atomic size, smaller atoms can have smaller distance between them, increase attraction. Ionic charge, greater ionic charge can increase attraction between ions. Atomic packing, closer packing can reduce distance between atoms and contribute to strong bonding. So the hardness is not simply a number we memorize. It is connected to atomic structure and bonding of minerals. And remember one critical rule during scratch test: make sure you actually scratch the mineral. Sometimes testing minerals simply leaves a powder, make it the surface. That is not same thing as scratching. The other properties is color. Now we come to properties everyone noticed first. Color is easy to observe, but unfortunately color can be unreliable. Why? Because teeny amount of impurities or defects in crystal structure can dramatically change a mineral color. For example, corundum. Pure or relatively pure corundum can occur in different colors. Add chromium. When add small chromium on corundum, a corundum can become beautiful red gemstone. That is called ruby. Example, sapphire. Corundum containing certain impurities of iron and titanium. It may blue varieties can produce blue sapphire. Okay, ruby and sapphires are therefore both varieties of mineral corundum, but have different gemstone, sapphire and ruby. The other example is quartz. Quartz can occur in many colors. Amethyst is purple, citrine is yellow to orange, rose quartz is pink. The color difference are related to impurities, defect, radiations, and other factors. So imagine finding a purple mineral. Do not immediately say this must be amethyst. You need additional evidence. Color is a clue of minerals to identify it. It is not a final identification. And that leads us another visual properties, that is luster. Luster is describe how minerals surface reflect a light reflection of light on the mineral surface. When you look at a mineral under light, ask, does it look like a metal? Does it look like a glass? Does it look like a pearl, or does it look like a dull or earthy? Pyrite is commonly metallic luster. It is shiny, a brassy appearance. In one reason, it can be mistaken for a gold. And the other example is quartz. Quartz commonly vitreous or glassy or luster. Its surface looks like similar to glass. The other example is mica. Mica commonly pearly or vitreous luster, especially fresh cleavage of surface on the mica. The other is Calcite. Some clay minerals can have dull or earthy appearance. So luster helps us describe how the light interact with the mineral surface, but does not confuse luster with color. Two minerals can have completely different color, but the same types of luster. The other properties of the 7th one is strike. strike. Now we are going to perform one of the most useful simple test, that is strike test. Strike is a color of minerals in powder form. To test it, geologists commonly rub mineral across unglazed porcelain strike plate, and sometimes the result surprising. Example: pyrite. Pyrite can be brightly yellow or golden, but strike generally greenish black to brownish black. It may look like gold, but does not produce gold colored strike. Example 2 is hematite. Hematite can appear blacky gray or metallic gray, but the strike is typically reddish brown or to red. This is extremely useful for diagnostic property. The example is magnetite. Magnetite is commonly black. Its strike is also black. This can help distinguish it from minerals that look similar but produce different strike color. Here is key idea. Color describes a mineral itself. Strike describes a powder form. A strike is often more reliable than surface color for identifying opaque minerals, but there is some limitation. Very hard minerals such as quartz may not produce useful strike because they can scratch the porcelain instead of leaving powder. The other one is number 8 is specific gravity. Now imagine you have two mineral samples that you are about the same size. You pick up one, then you pick up the other. Suddenly you notice, whoa, this is much heavier or this is much lighter. This observation is related to specific gravity. Specific gravity is a density of a substance relative to the density of water. For example, if a mineral specific gravity 2.5, it is 2.5 times denser as water. For example, quartz has specific gravity approximately 2.65. Galena is much heavier, which is specific gravity 7.4 up to 7.6 specific gravity. The heavy fail is an useful field clue. Gold is extremely dense with specific gravity 19.3. That is why a small piece of gold feels surprisingly heavy for its size. The other example include lead approximately 11.3, silver approximately 10.5, copper approximately 8.9 up to 9. So if an unknown mineral feels usually heavy, specific gravity may help to narrow down its identity or differentiation. Specific gravity influenced by density and packing of atoms within the mineral structure. The other special minerals properties, we have now covered the 8 major physical properties, but geologists have even more tools. Some minerals have special properties that make identification much easier. Reaction to acid: some carbonate minerals react to dilute hydrochloric acids. For example, calcite reacts readily with dilute acid or HCl, produce visible bubbles of carbon dioxide. Aragonite, another calcium carbonate minerals, can also react with acids. Dolomite also like. And magnesium minerals responds or to a magnet or repel or attract. Magnet is strongly magnetic. So its name itself gives you clue. Pyrite can also show magnetic behavior, although its magnetism varies. Hematite is not strongly magnetic like magnetite. Also, some hematite specimens can show weak magnetic behavior. Magnetism can be useful additional diagnostic text. The other one is fluorescence. Some minerals can actually glow under ultraviolet light. For example, fluorite. Some fluorite specimens show beautiful fluorescence. The calcite, for example, certain calcite specimen can fluorescence in different colors. The Willemite Willemite is famous for strong fluorescence and can glow brightly under ultraviolet lights, but color and intensity of fluorescence can vary between specimens. The other one is radioactivity. The other properties to differentiate mineral is radioactivity. Some minerals contain radioactive elements, for example, Uraninite. Uraninite contains significant uranium. It can be radioactive. And Torbernite is a copper uranium phosphate minerals. It can contain radioactive, or it can be radioactive. Utonite, another uranium-bearing minerals that can exhibit radioactivity and fluorescence. Radioactivity should be detected using approximate or appropriate instrument and safely produced rather than by directly handling or experimenting when unknown radioactive minerals. Think like a geologist. So, can you identify minerals just by looking at it? No. Sometimes you can make a good first guess, but professional mineral identification requires multiple clues. Let us review 8 major properties one more time. Number 1 is crystal habit. What characteristics or shape does mineral develop? Number 2 is cleavage. Have seen, does break along specific plane. The other is fracture. Can it scratch a glass, knife, lead, or another minerals? Color. What the color does it appear? But remember, color can be misleading. Luster. Does reflects light like metal, glass, or something else. The other is strike. What color it powder form? The other specific gravity does feel unusually heavy for its size. And we have our special clue: acid reaction, magnetism, fluorescence, radioactivity, and phosphorus. The real powder come from combining these properties. For example, imagine you find golden metallic minerals. Does not immediately call gold. Check its hardness, check its strength, check its density, look at its crystal habit, and compare all of this evidence. That is how geologists approach to mineral identification. One property gives you clue. Several properties together you can give you best identification. So the next time you pick up strange rock of minerals, does not just look at it, investigate it, because of every minerals has a story of written in its shape, cleavage, fracture, hardness, color, luster, strike, and its density. And you just need to know how to read the clue. If you enjoy this lesson, subscribe to Geology Wonders for more video about mineral rocks and geology exploration, earth resources, and incredible processes that shape our planet. And tell me in the comment section which mineral's property is most useful for identification: hardness, cleavage, strike, or specific gravity. I will see you in the next Geology Wonder video. Bye bye.